Welcome back. Congratulations, you found the way back. That's the first challenge of this course, to find your way in this building. Just a warning, you are free to explore different routes, but there is some one-way function. So there is some doors you enter, and if you don't have a badge, you will never be able to get out again. So maybe it's best to follow the official route. It's your choice, but of course, or you can take a local student with a badge and they can help you. Okay, so before we start, after this lecture, there will be lunch for the people from industry. I will show up here. You can join me. We go to a restaurant across the street together. All the others, you go to the student restaurant and you have to have a voucher. And you can get this from Pela at the reception desk. Okay? But so the people from industry don't go to Alma. You can come with me. But the rest goes to Alma. So it's a pleasure to introduce the next speaker, Professor Vincent Rijmen, who will give you an introduction to symmetric cryptography.
Okay, thank you, Bart. So before lunch, there will be a lecture. And I'll talk to you about symmetric primitives. They are used for encryption and authentication. We first go through stream ciphers and block ciphers, which are, let's say, the workhorses of symmetric key cryptography. I will say a few things about modes of operation and then about authentication. So in the whole lecture of today, we actually simplify the world to a very simple world where there are only a few people living, namely there is Alice and Bob who want to communicate with one another, and then there is the eavesdropper Eve who wants to eavesdrop on the messages or who wants to modify the messages. And so eavesdropping is countered by encryption, and modification is countered by authentication. Yeah? And the way how we solve this is by introducing crypto boxes that convert messages or plain text into cryptograms on the side of Alice and that do the opposite operation on the side of Bob. And both of these boxes work with a key, which for the purpose of this lecture will be the same key between. So Eve and Bob will have the same key. And of course, in general, you need to think of a way how this is possible, how Eve and Bob can share the same key, but that's outside the scope of this lecture. Yeah? And so a first idea, let's say the whole lecture is about what we put in the purple boxes, the crypto boxes. And so the first idea is where we start from the Vernam cipher. What is the Vernam cipher? You take a key that is of the same length as the message that you want to transmit, and you convert them both to bits, and then you XOR bit by bit. And what you get out is the cipher text. Yeah? If you have a secure key, so an unpredictable key, then this encryption method is what we call perfectly secure against eavesdropping. So there is no way that an attacker can actually learn anything about the message if he doesn't know anything about the key. The disadvantage, of course, is that you need a key that is as long as your original message. And as I said, you need to get it to the other side, and you need to generate it. And so history is full of stories where people made mistakes in the generation of this key, and then you lose the security. You know? But nevertheless, people have been thinking and tried to actually come close to that situation, but without really having to generate the long and random key. And how can you avoid that? Is, well, you start from a short random key and you think of a way to expand it. And in terms of systems, electronic systems, we talk about a finite state machine. That is, we have a state machine here that is initialized with some initialization vector that can depend on the key, that updates itself. We have a state update. In every iteration, we update it. And then some part of this internal state goes to an output function, and out comes a stream of bits. Yeah? And so, in general, we can make the initialization value depending on the key, we can make the state update depending on the key, and we can make the output function depending on the key, or we can take some of these parts constant and public and let only other parts depend on the key. That depends on how we design the stream cipher. And so the output bits here, like in the Vernam cipher, are bit by bit XORed with the plain text to get a ciphertext. And so the receiver, Bob, does exactly the same and XORs again this output to the ciphertext. And if we XOR the same bits twice, we know that we get the original plain text back. So what's the big problem with all these mechanisms is that you should never reuse the output here. If you have two different messages that are encrypted with the same output here, then an attacker who knows this or who suspects this can XOR the ciphertexts. And if you, and I have it on the next slide, if you look at two different ciphertext bits that have been, that by the same key bit was used in XORing the ciphertext bit, you actually cancel the key bits and you get the XOR of the plain text bits. And if the plain text contains a little bit of redundancy, can just be it was written in a readable language. That's already enough redundancy to be able to split this XOR in its two parts, and then you can decrypt. And so in all these war stories of Second World War, actually more during the Cold War, you have failure of systems because of this. So perfectly generated random key, but reusing it in order to save on the cost of generating the key. And then people who know that or who suspect it can just XOR cipher. And you can automatically XOR a lot of ciphertexts with one another. And then when you see something coming out that obeys the right statistics, you know that you hit jackpot. So that's in fact why in modern ciphers we have this initial value. So in the old days, this initial value was typically a constant. But nowadays we know we have to vary, that for every new message you should have a new initialization value such that you always generate different keys. So that means that a typical stream cipher nowadays performs some key setup. That's typically a rather long process from the short random key to define the whole state update and the internal state in a complicated way depending on this key. Then for every new message that you want to encrypt, you have a setup of the initialization vector, different for every key. And then you generate key stream to encrypt the bits. And usually a stream cipher gets its performance, its speed, by making the third step very fast. And it gets its security by making the first two steps very lengthy and complicated. And so one tries to get high speed combined with high security. It's not always successful, but we'll see some of the examples. So, and one component that often occurs within a stream cipher is what we call a linear feedback shift register. So this here is a register where every cell is a bit or a byte or a word, depending on the design. And in every clock cycle, we shift the contents from every cell one step to the left. What's here at the left drops out. And on the right, we shift in a linear combination of some of the cell's contents. And so part of the design is which cells you should combine in order to get good properties here. There's a whole theory about it, how you have to select them. It's related to divisibility of polynomials and stuff. And if you do that well, you can have some interesting properties. But let's say the main problem that these constructions have is that a linear feedback shift register in the end is a linear system, which means that an attacker can actually easily break it by writing out a system of linear equations and solving for it. So we need to add something extra to make these equations non-linear. And there are several typical combinations. One is that you, instead of just having one linear feedback shift register, you have several, and you take the output from each of them, and then you do something nonlinear with the outputs. Or you put one large linear feedback shift register, and you take several of the states elements and you combine them in a nonlinear way. Or you do what's called clock control. We'll see an example of that, is that you make the updating of the shift register irregular, and then the equations also become nonlinear. Yeah? And so the most famous example nowadays is the A51 stream cipher, which was in GSM. It's now, I think, nowhere used anymore, but it was ubiquitous for a while. So it consists of 3 LFSRs, yeah, with different lengths. That also follows from the theory that you should have LFSRs of co-prime lengths. So it says 18, it actually has length 19, because we start counting from the 0. So we have 19, 22, and 23, which are co-prime numbers. And so in every clock cycle, the software checks the contents of the yellow cells. In every cell is a bit. And so it checks the contents of the yellow cells, computes the majority function, and then only the circuits, only the LFSRs that agree with the majority are updated. Yeah? So if they are all 1, so they all agree, or they're all 0, they all agree, so they all update. Otherwise, if it's 2 against 1, only the 2 in the majority update, and the one that's in the minority just keeps its value. So that gives the stuttering in the clocking, makes the equations nonlinear. And how is the output bit computed? Is just the XOR of the 3 bits on the leftmost side. Yeah? So the output function here is linear, but the update function has been made nonlinear by introducing this stuttering. Yeah? So this was broken. Yeah? It's in particular also the implementers weakened it even further by initializing it with too many zeros, but we don't have the time to talk about that today. So this is another example, the Bluetooth stream cipher E2. It has 4 LFSRs, which are now just shown as blocks here. Again, the outputs are XOR to produce the output stream, but in order to introduce nonlinearity, there is an extra building block here, yeah, you see, that takes as input also the outputs of the LFSRs, does an addition, divides by 2 here, and then also has 2 table lookups, which are based on components of the AES and which are nonlinear, and so which introduce nonlinearity into the system. And then we see that the output of this block is also going to the output here, XORed here, such that the output of the stream cipher, you could say, is a sum of some linear function and a nonlinear function, so the end becomes nonlinear. Yeah? And so why do people insist on having the linear components? Is because linear components can be designed to have a long period, so a very lengthy period of time before repetition occurs. Yeah? And then actually we have no proof then if you add something nonlinear that you still have this lengthy cycle, but there is a kind of belief or hope that adding the nonlinear part will not reduce this length by any significant fraction, but that it definitely adds complexity, adds nonlinearity to the equations. Yeah? So these are 2 examples of LFSR-based stream ciphers. Another popular example is RC4. It's now a rather old cipher, but you can still encounter it. Originally, it was secret, but then the design was leaked. And it's based on permutation shuffling. Yeah. So how did it work? I'm explaining how it works, although it's old because newer designs of stream ciphers kind of reuse several of these ideas. So it says we start with a table with 256 bytes in it, ordered from 0 to 255. Yeah? So you have every value occurs exactly once in the right order. Yeah? So that's how the cipher is initialized. And then we have a pointer j and another pointer I. And then at every iteration, the I pointer is increased by 1. It's in the for loop. And the j pointer is increased in this way. So you add the element at position I in your table, you add a byte of key, and you add that to the content of the j pointer. All these additions are modulo 256. And then you will swap two elements in the table. Yeah? And you do this, so 256 times. And so afterwards you get a table that, or let's say, like a deck of cards that has been shuffled depending on the value of the key. I also have a kind of animation for that. So imagine that at some point in time, your I pointer is here, your j pointer is there, and you already have been shuffling a bit. And so the top row are the addresses, the addresses, and the bottom row are the values that are currently at these addresses. So then the I pointer will be increased by 1. We look up the element, which is 92, so the j pointer is increased by 92. And then we swap. So this was what's described on the next slide. Now, we're already here on the next phase, where we will no longer include key, but we'll start producing output. What we do then is, after the swapping of the elements, we will add the contents, so 162 plus 92, look up, so we get 254. We look up the element that is there, and that's the output byte. And this is repeated every clock cycle to output 1 byte every time. So during key stream generation, we continue with the swapping and outputting 1 byte. And the idea of continuing with the swapping is that, of course, every time you output something, an attacker can write out an equation and start to make findings about what's in the table. But if you keep on updating the table, then the attacker forever runs behind, because he gets some equations about the table, but it's, by the time he has a significant number of equations, the table has changed already a lot. And so people have been trying to break this cipher. So what are the weaknesses? The most important weakness is that this cipher has been implemented a lot with 40 bits key, because it dates back from a time that the United States didn't want to allow export of software with keys larger than 40 bits. And of course, in theory, a company that implemented RC4 could make 2 versions, one for inside the USA and one for exporting, but that would mean 2 different versions of the software, and that's what managers don't like, because it's double cost of maintaining, so they just had 1 version that could be used both internally and externally. And of course, you never update software unless it's really broken. So we still find leftovers of that. A second weakness is that this shuffling is good on average, but it's not always good. For some values of the key, you actually, after you have shuffled the cards, not all the cards are in a random position. So an attacker can do some analysis and see that for quite a number of keys, initially, he can predict what's in the table, and in particular, he can predict what will be the first bytes of key string that you generate. And then a final weakness is the fact that there is no IV input. I mean, this design dates back from before the time that it was customary to have initialization vector input. It was used later when people said, well, we know now we need an initialization vector input, but there is only a key input to the cipher, so why don't we split the key in 2 parts? One part is the key, the other part is an initialization vector, and we run it like that. But that was not how the original designer intended its use. And so if an attacker can observe output that was generated with the same key and different IVs, you can again write out equations and solve. And that was how the cipher was used in the web protocol, and that's why one of the reasons why web was completely insecure, because the stream cipher was used in a way that was not intended by the designer. Yeah, okay. So those are the stream ciphers that I think you should know about. And now I'll switch to my favorite topic, the block ciphers. Block ciphers you could think of as a way, you can most easily think of them as something that grows out of what I call the Boy Scout cipher. So the Boy Scout cipher consists of the methodology that you encrypt character by character in your message. So you have a message, and you will replace every character by another character. And so your key is the table that describes how the green characters in the message need to be replaced by the red characters. So the example here is you want to encrypt the word bed. You look up, you see the B becomes an I, the A becomes a U, and the D becomes a T. So IUT is the encryption of bed. And so this type of ciphers can be broken by frequency analysis. I put here the table that you can find in Wikipedia. And it's also explained there how you do this analysis. You compute the frequency of the characters in your ciphertext. And if you know the frequency in your plain text, then you can start to match values. Because in English, the most occurring character is an E. So the symbol that you see most often in your ciphertext probably encrypts the E, and you can work your way down. And if you implement something like simulated annealing or so, this thing you can have automatic decryption very easily. And if you don't know what the original language was, then actually by just looking at the shape of this distribution here, you can derive that, because every language has its own characteristic shape. And this was what cryptanalysts in the 18th and 19th century did, actually, solving this type of ciphers by hand, knowing the distributions for Russian, for French, for German, for English. So by itself, this is not secure, but actually it's not very far from secure. We can make this secure by taking one simple step, and that is, instead of substituting character by character, we will group characters in blocks. So I've shown here the example where we make groups of 4 characters. So instead of an alphabet of 26 characters, we now have a kind of super alphabet with 26 to the power 4 possible symbols, because every symbol consists of 4 characters. And then, again, in principle, you define a table with the top row is all the possible values for the 4 character blocks, and then you define a random reordering, a random permutation, and that's the blocks at the bottom. That's your secret key, and you replace block by block now. This is actually what's called a code book, is this principle. And if you make your blocks large enough, then this becomes secure, because you make the frequency analysis infeasible to do, because your number of bins starts to grow. Also, so the most frequently occurring characters are now spread over many different blocks, because this E that occurs all the time in English occurs now in many different blocks, and so the peaks of the distribution, and these peaks here, are now spread out over many different blocks. And also, if your message is less than the square root of the size of this table, then it's actually very unlikely that you will see the same block more than once. So even if you could do statistics, you need a very large amount of plain text, of ciphertext, to start to make meaningful statistics. So it becomes secure. What's the only disadvantage of this generalization is that this table becomes large, of course. If my block length grows, this table size also grows, and it grows exponentially in the block length. Yeah? So we want to actually avoid this table. We definitely don't want to transport it. And as I said, in symmetric key cryptography, the receiver typically needs to get this key in some way. And you don't even want to store it locally because it's too large. So instead of really generating this table randomly and storing it, we will introduce some kind of a function that computes the table elements. Yeah? So the row here, this second row, we will not explicitly store it, but we will compute it on the fly when we need it by means of a function that we still need to define. Yeah? And so this function takes as input the block of characters, if you want, and some secret key. Yeah? And so this function that we now need to decide upon should have two properties. It should be fast, computable, because we will compute it all the time, and it should be secure, meaning that we don't want that someone who sees outputs can invert this function and get back the X and or the key. And so this function f, that's actually a block cipher then. And so Claude Shannon, the founder of information theory and also the founder of cryptography or public cryptography, proposed to design these block ciphers like shown here, because he said what you want typically is that something is fast both in hardware and software and can be set up quickly. So he said the cipher should be a combination or a product of two types of components. We have the blue blocks here. The blue blocks work on one character at a time, so they're like the Boy Scout cipher. But you add an extra component that he called diffusion layer that mixes outputs of different Boy Scout ciphers, somehow mixes them and produces again now. So this could be rewiring, where you shuffle the wiring of the bits, or could be any other linear operation that has, in this case, 4 inputs and 4 outputs. Yeah? It was very quickly realized that if you do just this, exactly like Shannon described it, the equations are not complicated enough. Attackers can actually write out the equations and solve for them. But no problem, how can we solve that? Shannon said, we simply add another diffusion layer and another layer of blue boxes, and then the equations get that more complicated. For modern usage, this would still be too weak, but the idea of how to get it secure is obvious. I think you just keep on repeating the green mixing layers and the blue substitution layers until in the end these equations are complicated enough. And that's where we get the concepts of rounds in a block cipher from. So every application of the blue boxes and the green diffusion layer is called one round. So that's why modern ciphers have 10, 12, 14, 16 rounds, which just means keep on repeating this product cipher until you get something that no one knows how to break anymore. Yeah. And so that's what we call nowadays an iterative cipher. We have the plain text coming in, we have rounds, and we have the ciphertext coming out. Yeah? And we typically, the rounds are a public described function that takes as input the output of the previous round, and also it takes as an extra input some value derived from the key. Yeah? And we call these things the round keys, and they're derived from the cipher key by means of a key schedule. So that's how block ciphers work. There are two popular structures. The one on the right is actually, it's like Shannon originally proposed it. They're now called substitution permutation networks. The one on the left is a variation that's called Feistel cipher, after one of the inventors. Yeah? And so instead of having exactly this structure, it says, well, split the input in two halves. The right half is used as input for, let's say, for the blue boxes and the green mixing layer. Then the output is bit by bit XOR to the left half, and then we swap both halves. So you see that the values of the right half actually are just copied to the left half in the output. It's only this output that gets actually modified. What's the reason for this special structure? It makes the round transformation an involution, so it makes it its own inverse. That means if you live in the 70s and the hardware that you can design is still very simple, let's say, where you have gates that have to be hand-wired to other gates, then you have to implement only one round, and it can do both encryption and decryption. So you don't need a separate circuit for decryption. You can do it with the same circuit. You only have to change the order of the round keys. So that was seen then as a very important advantage. Okay. If you look at modern block ciphers, almost all of them either use the Feistel structure or this SP network. So what are the differences between the ciphers is, you could say in the details, in which substitution blocks you exactly choose and how you implement the diffusion. And there the goal is always to keep security and make it fast. And you have then a trade-off. Do you want a complicated diffusion layer, for example, which is a bit slower, but maybe you need less rounds then, or you can make it very simple so that every round is very fast, but then maybe you need more rounds to have it secure, and every designer has a reasoning on what's the best trade-off between these two. Okay, then the two most important examples. One is the data encryption standard. So it works on blocks of 64 bits, and the key length is 56 bits. It uses 16 rounds. So it started its life as a FIPS standard, which means standard of the United States government for protection of data that is sensitive but not classified. But in practice, it has been used everywhere in the past, because it was the only standard for encryption. So everyone copied it in his own standard. And so it has this Feistel structure that we see here with the swapping and the output of the right-hand side being input to several transformations, then being bit by bit XORed, and then the swapping. There was some extra stuff added, an initial bit permutation and the reverse at the end here. It's not clear what purpose this serves, because it's a fixed permutation of bits, so an attacker who sees the ciphertext can always invert this step, because he knows exactly what he has to do to produce this output here. So there is no real cryptographic benefit. Some people claim that it was added to make software slow compared to hardware, because in the hardware of that time, such a bit permutation was just a matter of how you connect the wires, which was at that time cheap. And in software, it's a lot of operations to do, and so you make software comparatively slow to hardware, and if you are a government, it's much more easy to control the export of hardware than the export of software. So you have better control on what countries can buy encryption. But that's a rumor, we don't know it. I have a few slides that show the inside of these components. So we actually will now look what's inside these parts here. And you see here, so what comes inside, we see 32 dots, that's the 32 bits, 1/2 of 64 bits. The E part is expanding the 32 bits to 48 bits, just because some bits are copied once and other bits are copied twice. Yeah. That all these circles mean XORing bit by bit every time with one bit of the key. So you take 48 bits of key, you XOR them with these bits. And then you have 8 different nonlinear blocks. Each of these blocks takes 6 input bits and produces 4 output bits. And then those outputs are shuffled or permuted in some way. In the original description of the standard, none of these components was motivated or explained. So, because the NSA at that time was very worried that just by publishing the standard, you would actually teach civilians how to make strong encryption. You would leak the knowledge. And so they didn't want to explain definitely why these blocks were chosen like this, because that's giving even more information. Yeah? And so for each of these S-boxes, as they're nowadays called, there was a description in the standard like this. It said, look at your input. It consists of 6 bits. There is a matrix here, and the 4 middle bits determine in which row, in which column you have to look, and the 2 outer bits determine in which row you should look. And then the number that's listed there is always a 4-bit number, so that's the output of the S-box. And so there were 8 different S-boxes. It's not so clear why they had to be all different, and why you couldn't use 8 times the same. It was immediately obvious that in all these tables, in every row, you see each 4-bit value once, which cannot be coincidence, of course. It was on purpose, but they didn't also explain why they wanted to do that. Yeah. And so there was a lot of controversy about this, whether this was hiding some trapdoor or not. But in the end, the cipher was broken by Moore's law. Namely, it had only a 56-bit key, and after a while, it just becomes too cheap to just trying out all possible keys. Yeah? And so for a decade, academics have been arguing about, or maybe 2 decades even, about whether 56 bits is just enough or not enough, until finally the Electronic Frontier Foundation spent $250,000 to build a computer that could do only one thing, namely searching for this key. They called it Deep Crack. So in 1998, they spent this $250,000. So 1/2 was spent on the real hardware, and 1/2 was given to the designer of the hardware. And this machine could recover a desk key on average in 50 hours. Nowadays, a couple of PCs do the same, but for that time it was fast. And so, nowadays, key lengths, if you want to keep something secure, don't use less than 64 bits of key. If you want a couple of years security, 80 bits is recommended, and 100 bits is a safer choice. Okay, so if DS is not good, what can you do? So a first fix was to use what's called triple encryption or triple DES. So you encrypt something with 1 key, then you apply DES in reverse with the 2nd key, and then you encrypt again with the 3rd key. So the original standard left here for the middle block 2 options to put DES in forward or backward operation. If you put it backward, like it's shown on the picture, it has the example that if you choose the first 2 keys equal, these operations undo one another, and you have again the single DES operation, which you could say is beneficial during a transition period. If you have a large installed base, you can update the hardware piece by piece, and only when everything has been updated, you start to encrypt with 2 different keys here. The big disadvantage of this construction is that it's slower. It's 3 times slower than DES. and also that the block size remains 64 bits. Yeah. And I quickly went over it, but as I said, we get security if the messages that we encrypt with the same key, if the total length of these messages does not get larger than the square root of our table size. We'll actually see a bit later a slide that explains where this limit comes from. But if you have 64 bits, the square root of that is 2 to the power 32 that's the square root of your table size. So that's only a couple of gigabytes, yeah? Which, again, in the 70s was a large amount of data, but which nowadays is what you maybe encrypt every day. And so you can encrypt 3 or 5 or 7 times. That doesn't solve that problem. So it was time for a new standard, and that was the AES. So the AES, Advanced Encryption Standard, looks again much more similar to the original Shannon cipher, in the sense that it applies the nonlinear building block to every input, to every bit of the round input. It works on inputs of 128 bits, and 128 bits is 16 bytes, so that's why you see 16 iterations of the blue block here, because it maps 8 bits input to 8 bits output. And then after the S boxes, there is a shuffling of the bytes, and then there is another operation which is called mixed columns, which I will also explain on the next slide. And this is repeated 10, 12, or 14 times, depending on the length of the key, 16, 24, or 32 bytes. The original Rijndael design had not only variable key length, but also variable size of the input, but standardized in the AES standard was only the 16 bytes input, 128 bits. And if you have 16 bytes, they can also be represented as a 4x4 array of bytes, and this is what's chosen in the standard description of the cipher. And so the step that applies the S-box just applies it to every byte of the input, always the same one. There is a mathematical explanation of how it was designed. It's based on the multiplicative inverse in a finite field, because one can prove that this has optimal nonlinearity properties. And then there is a small affine step to remove the regularity a bit. Then the mixed columns step works on every column in parallel. It looks at a column as a vector and then multiplies the vector by this matrix to get again a 4-byte vector out. Yeah? And these coefficients here have been chosen from an error correction code that guarantees that if one bit changes at the input, then all bytes at the output will change always. If bits in exactly 2 of the input bytes change, then always at least 3 output bytes will change. So you have this distance property that number of changes at the input plus number of changes at the output is always at least 5. Yeah? So that guarantees diffusion of small differences. Then the shift row step, which was this rewiring, if you describe it on matrix level, you get the fact that every row is shifted over a different offset. Yeah. And then the key addition is simple matrix addition. Yeah. So that's the AES. I will now talk about modes of operation. The modes of operation is the study on, once you have a good block cipher, how should you use it? Yeah. Block ciphers have been used primarily to encrypt, but they can also be used to authenticate. then you also need another mode of operation. And they've also been used to prove security. And so a security proof actually investigates, says, what if the block cipher itself would be perfect? How do we have to use it to make sure that also messages that are longer than 128 bits are also well encrypted? Of course, in reality, a block cipher is never perfect. And as a pure mathematician, you can say, well, then you have proven nothing, because your proof only holds if the block cipher is perfect, and then you can prove things. And if it's not, then you don't know. But still, we use that because the hope is that if you use an imperfect block cipher in a mode of operation that would be perfect, if the block cipher was perfect, you still have good security. I first show some examples of bad modes of operation. So let's say the straightforward mode of operation is what we call electronic codebook. So it's exactly what I described. You use the block cipher as a kind of codebook that computes for any input block the output block. So this is like the generalization of the Boy Scout cipher. Replace every input block by an output block and compute it by means of the block cipher. So what's the big problem is that if you encrypt data that has structure, for example, an image, and you encrypt it, you will get something where one-on-one you cannot know what the value was of this original, of this one pixel here, but by looking at the ciphertext, you still see the structure. And in this case, you still see that it is some encryption of the penguin. And for other types of data, because same input blocks go to same output blocks, redundancy in the plain text is translated to redundancy in the ciphertext and leaks. So that's why you should never use it like this. And so that's why many products, in particular old products, but use cipher block chaining, which is a simple fix to the problem, and where you say you do not just encrypt, let's start here, you do not just encrypt a block, but before encryption, you XOR it with the output of the encryption of the previous block. And so you can see that even if P1 equals P2 equals P3, C1 will be different from C2 and from C3, because what goes into the block cipher is this block XORed with something else. And then, of course, you need to do something special at the first step, because you cannot XOR a previous block. So you can add there an initialization vector, which you typically then also want to choose different for every message, such that even if you encrypt the same message twice, an attacker will not see it from the ciphertexts, provided that you make sure that the initialization value is different every time. Because if you choose the same initialization value and the same plain text, of course, you will produce the same ciphertext blocks. So this mode of operation is good, but we can see here it still has problems if the amount of blocks that you encrypt approaches the square root of your table size, and that's on the next slide. So we assuming that you're encrypting a very lengthy plain text, so cut it in blocks of 128 bits and encrypt it with the CVC mode. And from the birthday paradox, you know that if you just look at randomly generated values out of a given set, after about the square root of the number of possibilities, you will have a repetition somewhere. I don't have to explain the birthday paradox, I think. Everyone knows it, yes. So this will also happen here. If we say this AES encryption is like just randomly generating 128-bit blocks. If you do this to the power 64 times, there will be 2 ciphertext blocks equal. We don't know in advance where they will be, but a repetition will occur. And once we have observed it, we know that the output of the AES in both cases was the same. That's the collision that we see. But because AES is invertible, any block cipher is always invertible, we know that if the outputs were the same, then also the inputs must have been the same. Yeah? And we can write out the inputs. So the input here was this plain text block XORed with this ciphertext block. That's also on the left here. And here the input was this other plain text block XORed with this other ciphertext block. Yeah? Now, ciphertext blocks are known, so I can move them to the left and the unknowns to the right, and I get an XOR of plain text blocks, which is the same problem as I had at the start of the lecture with the Vernam cipher if you reuse random key, and that you XOR blocks, and if the attacker already has some knowledge about the blocks, some statistical information, you can start deriving the values of the plain text blocks. Yeah? And the thing is that if you encrypt slightly more than the square root of the blocks, then the number of collisions rapidly increases. Yeah? So if you, for example, have 2 times this value, there will be many of these equations that you can write out, and very quickly an attacker can solve for the plain text without breaking AES or without recovering the key. Yeah? And so this was why we couldn't live with the DES and its short block length anymore, and why AES has a 128-bit block length, because encrypting 2 to the power 64 blocks with the same key, that's quite a large amount of data. Yeah? So that will not quickly happen in practice. Another mode of operation that is quite popular is the counter mode. Counter mode actually is taking a block cipher and using it to build a stream cipher. So what you do is you take some counter, starting from some value that you can choose. Maybe you can put initialization vector somewhere in here as part of this counter, and then you will encrypt the counter value, and what comes out, you will XOR with the plain text to get you the ciphertext. And then you increment the counter by 1, you encrypt the value again, and what comes out, you will XOR with the plain text to get the ciphertext. Yeah? So this is a stream cipher where the state update is very simple. It's just incrementing the counter. Yeah? I have put here incrementing by 1, but you can also increment by any other number, preferably an odd number, because if you always increment with an even number, yeah, then you know that the 1 bit will always stay the same. But actually, you can also even do that. The block cipher is big enough to take this. And then so the output selection function, which I had initially, is now the whole block cipher, yeah, depending on the key. And it produces something that you can XOR. So this has the advantage that even if you go over the square root, there is no repetition of the outputs here. Yeah? So we don't have this problem. Yeah? So that's good here. On the other hand, people say that's actually not good, because from seeing that you don't have this problem, you know that this is not a random function. Yeah? That there is, you know that someone was using the block cipher in counter mode. Because if he would have been using the block cipher in CBC mode, there would have been a collision. I would see the collision. And I don't see it, so I know something, namely that you're using the counter mode. So people try then to even get rid of that. Okay. And I made a slide briefly comparing block ciphers with stream ciphers. The big advantages of stream ciphers are the extensive theory that exists mostly about LFSRs. But as I said, in the real designs, we always step just beyond the LFSRs, because only LFSRs are linear and hence breakable. So you always need to just step outside this theory to get a possibly secure cipher. But they're always made small and fast, and you don't need an extra mode of operation. For block ciphers, you need a mode of operation. There is less theory, but nevertheless, the public standards are typically block ciphers. They're designed with a high security margin. There are many different modes you need a mode of operation, but there are many different modes of operation to get you different properties. And so they're used a lot in practice. Okay. Then I will now talk about symmetric authentication. So in authentication, the idea is to protect a message against modification. By protecting against, I always mean that the receiver will notice if something has been modified. Because an attacker can always modify a ciphertext. We cannot avoid that, but we can try to detect when it has happened. So that's what protecting here means. And we'll typically do that by computing some kind of fingerprint, digital fingerprint of the information by using a hash function, and then protecting this hash. So it's a two-step process where we say if you change something to the message, then also the fingerprint will change. And I have a special operation to detect modification of the fingerprint. And so the workhorse there is what we call a hash function. So a hash function is sometimes also called irreversible compression. So you have a large input that you compress together into a string of 128 bits, 256 bits, very short, where you hope that you can make this somehow unique. You know, in theory, it cannot be unique. If you have as input something that has a length of, that is larger than what can come out, then there must be several inputs going to the same output. That's pigeonhole principle. If the number of outputs is smaller than the number of inputs, at least two inputs need to go to the same output. But you want that this mathematical fact cannot be exploited, that you don't know, that no one knows a way how to, in practice, compute two inputs that go to the same output. And this intuition is translated into more precise notation in different ways. So one property we require is what we call pre-image resistance. That means that if you are given an output, it should be very difficult to find the corresponding input. So you cannot follow the red arrow. From the output, you cannot go back to the input. Collision resistance then means you cannot easily find two inputs that go to the same output. And then there is a variant of that, which is here in the middle of the slide, which is what's called the second pre-image resistance. That means if you are given an input and the corresponding output, difficult to find a second input that goes to the same output. So it's a property similar to collision resistance, but different. Because in the collision resistance, it's, as an attacker, you're completely open which inputs you choose to find some output that you can also choose. So find any two inputs that go to some common output, whereas in the second problem, someone has already given you an output and a corresponding input, and then says, find now a second input that goes to this output. So this actually is a property that you require if you have signatures on electronic documents. If someone gives me a digital contract and I put my electronic signature on it, then it should be very difficult for an attacker to produce another contract that maps to the same output which I then sign. That would be, if someone can do that, then you cannot have electronic contracts. In theoretical, or let's say symmetric cryptographers always try to ensure this property, because if you can ensure this, that it's difficult to find this, then these and these will be even more difficult. But in practice, it's often sufficient to have only that property. But as I should stress, information theoretically, it doesn't make sense, because pigeonhole principle says more inputs than outputs, then there must be two inputs going to the same output. And also the concept of given the output, difficult to find the input. In information theory, that doesn't exist. Because an output, you can find an input that goes there. Even in complexity theory, there it would be possible to have such type of primitives, but in practice, we never use constructions where we have complex theoretic proofs for. So we always use block ciphers, basically, to get these properties. Okay. Yeah, these are just the generic attacks. So if you're given an output and you have to find the corresponding input, you can always start guessing. And then probability theory says that if you guess long enough, after some time, you're bound to find a good output. And so typically, let's say, you can be right the first time you guess. You can be very like a person, and someone gives you an output, and you guess an input, and it computes that output. Or you can be very unlucky, and you have to try very, very many trials before you hit the right output. But mathematically, we can compute the distribution of this and can say, well, the expected number of trials is 2 to the power n minus 1 if n is the size of the output. So there are 2 to the power n possible outputs. After half of that trying, you are, well, that's the expected number of trials you have to make. For a collision, there is the birthday paradox that says actually, if you try to square root of 2 to the power n times, then there's a high probability that 2 of them will match to some common value that in a collision attack you didn't have to specify in advance, so then you have success already. So that means that if we want to design a function, these are kind of the upper bounds. We don't have to try to be better than that, because we know someone who doesn't look at the construction can also always do this type of attack. In cryptography, we use 2 types of hash functions. No, actually, we talk 3 types. 2 types is they can involve already secret key during the computation, or they can have no secret key in the computation. If they have no secret key, that's the green one here, then we talk about manipulation detection codes or short hash. If we use a secret key, then there are 2 popular construction methods that I will talk about. One is the message authentication codes, or MACs. Another one is based on universal hash functions. And what we often have is, because a hash function should be able to process an input of any length, that's a bit difficult to describe a function where you don't know the size of the input in advance. So that's why we split up this in 2 parts. There is one part that we call the compression function that has a fixed size input to a fixed size output. For instance, it can take inputs of 1,000 bits and it produces outputs of 500 bits in a fixed thing. And then there is an extension method, a mode of operation, if you want, that says now, given a message of any size, how often and in what way do you need to call the compression function in order to get your fixed size output? I'll give an example on the next slide, which is the tree method. So the tree method says, take your message and cut it in blocks, let's say, of 1024 bits, and then apply your compression function to compress 2 blocks to 1. And do that with all your blocks. And then the next layer, you take the outputs of the previous layer, and again, you compress 2 blocks to 1. And if you do that enough times, then in the end, you will have 1. So that's one way to go. And then the number of layers that you have depends then on the length of your message. It's the logarithm, basically. So that's one way to do that. Another popular way is called Merkel's method that says you start from some fixed initial state. Again, you have cut your message in blocks, and you start with processing one block together with initial state, and that computes an output, which is then the first input for the next iteration, and then you add the second block. And then you proceed. And so you process your message block by block, taking the output of the previous step and adding a new block, and so on, and so on, and so on. If you do this, of course, you have to fix your IV. One can easily show otherwise that it's trivially possible to create collisions. But this is different from the IV in encryption, because if we use encryption, we always want different IVs. For authentication, we want fixed IV. I'm stressing it because I've seen implementations where it was done wrongly. Then there are issues with what should you do if your message length is not divisible by your block length here. If I say 1024 bits every time, and my message has input length 4020, then in the end I have a block that's not completely filled with bits, so I need to extend the message then to the next multiple of 1024. That's called padding. And then there are, initially people thought, well, we just add zeros, so that's maybe the naive solution, just add zeros. But then you can also show it's actually ambiguous if the message already ended in zeros. So how many zeros were there in the little message, and how many zeros did you add for padding? So the standards then describe a more complicated padding, typically like this one. They say, first add a 1, then go to the end and add there an encoding of the length of your input, and in between the 1 and this encoding of the length, you fill up with zeros. This again then means it's weakly dependent on the size of the input. There's a weak boundary there, because if you say, I will encode the length of the input, you need to specify how many bits you will use for that. And if you say 64 bits, then that means that your input can be at most 2 to the power 64 bits. Otherwise, your encoding has overflow. So I already showed some extension methods, the tree and the Merkle one, and then the only remaining part is how do you design this compression function. So there are, let's say, two main philosophies. One is based on a block cipher, another one is use a dedicated design. The ones based on block ciphers, one is shown here. So in particular in the 70s, when DES was the only standard available, people wanted to do everything with DES. So they said, well, take this encryption. So what we need for our compression function is it should be able to process 2 inputs, 1 block from the message and 1 output of the previous step. So take your DES, wire the output of the previous step to the plain text input of the block cipher, and instead of using a secret key, you take the new message block. And then you output the ciphertext, and then you add a feed forward, XORing the input to the output. That's to make this non-invertible, and then this gives you the next output that in the next step you will then encrypt again, but now with the next message block, and so on and so on. You can do that. It's slow, but it can be done. Then after this initial design, people found some variations that I've shown here. They said, well, you can also switch. So in the previous slide, I had the output of the previous step on the top and a new message block coming in here. You can also switch them. Or you can do that, but then you can also add the feed forward here. So that's basically the three ways how you can take a block cipher and use it in a hash function. So what are the disadvantages? This is slow, because you go as fast as the block cipher only, and the block cipher needs to update its key every time, which makes it even more slow. Also, a block cipher like DS has only 64-bit output, which means that a collision attack takes a number of trials, about the square root of 2 to the power 64, so 2 to the power 32. So that's not a very large number. And also, well, you can use a block cipher for this and think that that's a good practice, but actually, originally, the designer of the block cipher was maybe not intending that you would use it in this way. So it could be that a block cipher is secure if you use it in CBC or in counter mode, and insecure if you use it like this. Yeah? That's more a theoretical argument, let's say. But anyway, then in the 90s, Ronald Rivest said, okay, I will do better. I will make a dedicated design. So I will, just in general, define a kind of state update, where the input state is the output of the previous step, and I produce the input of the next step. I will process message blocks, and I will have this feed forward. And so this will be very different from a block cipher. Well, if you look inside this state update here, the proposal was like this. Yeah. What we actually see is, again, a kind of Feisel cipher, but instead of splitting the input in 2 blocks, we split it in 4 blocks, and we use 3 of the blocks as input of some function, and we XOR the output to the remaining block, and then we swap the order of the blocks. Yeah? So also these so-called dedicated designs actually look very much like block ciphers, but not a DES, but another block cipher. Yeah? And so this was his MD4 cipher. There was then later the SHA and SHA-1 standards, which you see they're not so different from the original MD4, but they add 1 block at the input, so they make the input longer. They do a few more operations, but it's like that. And then there is the SHA-256, which was the next standard, which still looks very much like that, but now instead of just modifying 1 block, like here, we modify the one on the left, and also we modify something here. Yeah? And we add a bit of complexity. So all these ciphers in what's called the MD4 family, all these hash functions, they're actually inspired on the previous one and adding stuff. Why did I do that? Because first this was broken, yeah. Then this was broken, so this is now not broken yet, but as cryptanalysts advance, then the designs are getting more complicated. Okay. How are these hash functions used then to authenticate messages? Well, you have your message, you use it as input of the hash function, you compute the output, the receiver does the same, takes his input and computes his output. We assume that you can get this output in some secure way to the receiver, like you read it over the telephone or something, and if there is no match, then the receiver knows that for sure something has changed at the input. If there is a match, then we assume that no change at the input has occurred, because our hash function is in such a way that it's not possible to find the inputs, and not practically possible to find 2 inputs that go to the same output. Yeah? So here I made a change somewhere in the input such that the output has changed. So then you know that something went wrong. Yeah? But what's definitely still to be done is that this output needs to be protected. Because if you send this just together with a message over the same communication line, an attacker can first modify this, and then compute the output that should go with it and send it over, and the receiver will not notice anything. Yeah? So we have to secure this output. People sometimes said, well, encrypt this output and send it over encrypted. But if you do that, it's better to actually include the key already in the computation of the hash. Yeah? And then an attacker who modifies the input, and if he doesn't have the key, cannot produce the right output. So then, yeah. What can an attacker then do? He can still guess. Huh? So that's the second attack here. An attacker can always modify a message and modify the tag, and then hope that he's lucky that the modified tag matches the modified message. It sounds like a silly strategy, but if there is a lot of money to be gained, you can do that. For example, the SWIFT network that secures multi-billion transactions. Well, if your tag is, let's say, only 10 digits, then you have a small but not zero chance that if you modify the transaction and you modify the tag, that you could be lucky and the billions go to your account. And with one attempt, your probability of success is very low, but if you can try again and again, if the Swift architecture would just reject false messages and never raise an alert to a higher level, you could keep on guessing. Every day there is a new multi-billion transaction, and you can keep on guessing until one day you will be lucky. So that's why Swift actually checks how many tags fail, and if it's too many, then it will raise an alert and they will do something. It's the same reason why your bank card, after 3 pin tries, says, now you've guessed enough. I will escalate to the management system of the bank, and we will check if the card was not stolen. So that was the second attack. The first attack is, guess the key. An attacker can, of course, always try to guess the key and recompute the tag for the message. And if with his guess he recomputes the right tag, then he is quite likely to have guessed the right key. So that's why it says here, an attacker can do that offline. Whereas the second attack, guessing the tag, the attacker doesn't know if he has guessed the right tag, so he can just send it to the receiver and be lucky or not. But the receiver will notice an attack is happening. In the first attack, where an attacker guesses the key, the attacker can just do it on his own computers, and the receiver doesn't know that an attack is happening. So that's why you need quite a long key compared to the tag that can be shorter, because if an attack is happening on the tag, and by guessing the tag, you typically are warned by this as a receiver. Okay. How are these constructions done? Well, popular is the CBC MAC. So you take your message, you pretend that you're doing CBC encryption, but in the end you throw away all the intermediate ciphertext blocks. You only keep the last ciphertext block, and that's your tag. And then in order to make it more secure, what people often do is to say, well, this last step, I use a different key from the one that I used in all the previous steps. For example, this last key here is the inversion of the key here. Or I invert half of the key bits, something specified, such that it avoids that people will do some types of attacks. So this is CBC. There are many variations. Some people also say in the last step you should not do single encryption but triple encryption. Or you can do think of many things to do that. So that's a MAC based on a block cipher. You can also do a MAC based on a hash function. So this is the keyless hash function like MD4 or SHA-1. You want to make it dependent on the key. Well, you say, I have the key followed by the message, and I will hash that all together. And so then this output depends on both the key and the message. Other people said, well, maybe it's better to do first the message and then the key. There are things to say about both. But maybe better is then what's called envelope. You have the key, then the message, then the key again, and you hash that. There has been kind of discussions for a long time. In the end, people settled for the following method. They say, take the key at the message, hash it a first time, then take the key again, but again by flipping certain bits. It's not exactly the same key as the key there. And you add the output of the first hash function, and you hash that again, and then the output, that's your tag. This is called HMAC, so MAC based on the hash function. Yeah? So this is used on the internet everywhere. There's even some kind of security proof, but in the same way as for motor operator for block size, the security proof says if the hash function would be perfect, then this is also good. Yeah? But we don't know if the hash function actually is perfect. Yeah? Yeah.
Sorry, maybe I missed it, but why do you throw away half of the output of the CMAC?
Ah, here. Yeah, so if you output less here, I'm going a bit fast because I don't want to stand between you and the lunch, but it's to counter this attack that I said, the key guessing attack here, yeah? That you can do offline. If you output here only part of the ciphertext, then an attacker who guesses key here, yeah, has less information. So then there are many candidate keys still remaining. So many trials will then still produce the right 64 bits, and this is maybe the right key, or it's a key that by accident produces these values. Yeah. Okay. The universal hash function ID is kind of observing that says, well, in some sense, if we look here, this is quite wasteful because we use here a hash function where we put a lot of properties on its security. I would say it should be impossible to find pre-images, there should be no collisions, and the attacker knows everything there is to know about this hash function. It's completely public standard. So we require a lot of properties, and then in the end we use it with an input that is partially unknown to the attacker, the secret key. And then some people say, yeah, but if you actually know in advance that you're going to use this component with part of the input depending on a key, then we can actually be much more lenient with the security requirements, because we do not have to consider an attacker who can freely choose inputs and look at the colliding output. No, an attacker actually doesn't know part of the input, so then we can greatly simplify this design here and go to something much more mathematically elegant, where we can give better proofs. Yeah? And that's what actually the universal hash function is. It says, well, if you can guarantee that for every new input you use a new key, then it's actually sufficient to do something like it's written on this slide, where you have your key, you multiply it with part of the message. Actually, you split your message again in blocks, and every block is multiplied with an increasing power of the key. You sum all the values, and you add another key, and then the output is your tag. And if you use these keys only one time, actually this is secure against collisions per image and all that. And so the only thing that you have to add is some device that produces a new key every time, but that can be done by a stream cipher, where you have one fixed key that produces for every message that you want to authenticate some output that you can use as input key for this construction, and that gives you then a universal MAC. It's called a universal MAC, MAC based on universal hash. Good. Then I wanted to say something about sponges, because they're quite the hype nowadays. In a sponge, it was you take a cryptographic component, function f here, and there was originally used to make hash functions. They say in every iteration, You take the sigmas are part of the message that you want to authenticate. You XOR them into the state, and then you apply this permutation. And then you XOR in the following, and you apply the permutation. So this looks a lot like the Merkle-Damgard structure that I've shown before, except that here it's non-compressing. Yeah? This is an invertible operation all the time. And after you've input all your message block, like in a sponge that absorbs water, you've absorbed the whole message block, then you squeeze the sponge, which means you repeat this permutation, but you take output. Yeah? And that's then your output of your hash function, squeezing the sponge. Yeah? What is shown on the slide here is where you use the same component, but also you use the squeezing to output bits that you will XOR with the plain text to get ciphertext. So you use one component to produce a tag and also to produce key string that you can XOR to the plain text to get ciphertext like in the stream cipher. Yeah? And it's called permutation-based crypto because this function here is a permutation contrary to the hash functions from the past and before SHA-1 that all use compressing functions, not permutations. Yeah, that's what I put here as well. I'll skip that and I'll show you a few remaining modes of operation. So at the end of the presentation is modes of operation for block ciphers that combine encryption and authentication, because I typically want both. And so one example here is the CCM mode, and I wanted to show it to explain you that actually you already know how it works because it's a combination of the counter mode and the CBC MAC. So we see here at the top, let's this part. We see here the plain text blocks. Yeah. We look at the bottom first, and we see here a counter, some starting number, and then concatenated with a 1, with a 2, with a 3, and so on. That's encrypted every time, and the output of the encryption is XORed with the plain text to get the ciphertext. So the bottom part here that encrypts is ciphertext mode, and then the top part, I think I'll show like this here, is a funny way to display CBC MAC. So we see the plain text blocks going in and then encrypting every time. So this is another way to show the CBC MAC that I showed before. Let me go. This is, if you can see, if you pull this tight and you see the output of every encryption goes as input for the next encryption, and there is always plain text blocks being added in. So if I pull this so that all these arrows become one horizontal line, and I add the plain text from the bottom instead of from the top, then I get this picture again. Yeah? So that's the CBC MAC part. There is something here which allows to include headers that do not need to be encrypted but only authenticated into the whole thing. But that's the CCM combined mode of operation. Another one is OCB, which is actually a lot like ECB, plus an encrypted checksum. So what do we see here? We see here the ECB-like operations, the parallel blocks of the block cipher, parallel instantiations. But the input is not just the message blocks, but the message blocks XORed with some values. And also the cipher blocks are XORed with some values that depend on the position and that give you then ciphertext blocks. And so because these Z values are different all the time, even if there is structure in the message blocks, the structure is no longer visible in the plain text blocks. And the authentication tag is computed by just XORing all the message blocks together, encrypting it and out net. And then the final one is GCM, which also uses counter mode for encryption. So now it's shown here at the top, the encryption part. So we have the counter incremented, encrypted. The output is added with plain text blocks to get the ciphertext. And then the ciphertexts are input of a universal hash function-based MAC to produce the tag. Yeah. So this one is very popular, in particular because the special instructions on modern CPUs allow to do very efficient AES encryption and very efficient computation of this universal hash function. Yeah. So that's why this is very fast in software on modern CPUs, because all the instructions that you need have been included in the hardware. So it's a bit cheating maybe compared to other modes, but it's what's now. Yeah, I have one last slide on what are the new challenges in block cipher design. It's currently, everything is about lightweight. Lightweight can mean many things. We want block ciphers that consume less power or less energy, depending on the application. It's power or energy that is important. Low latency if it's for servers. Low complexity in hardware, low complexity in homomorphic encryption. By the end of the week, you will learn about homomorphic encryption. Sometimes we want to do a block cipher in homomorphic encryption, and then our metric for complexity changes, so then we want other designs maybe, or in multi-party computation. I believe you will also learn about that by the end of the week. Or low complexity in secured hardware implementations. So if hardware needs to be hardened against side channel attacks, it again adds complexity depending on how you design the block cipher, which again leads to other constructions. Yeah, that's it. I can take a few questions now, but not too long, I think. Otherwise, you'll miss the lunch. But if there are urgent questions, yes. Okay. Yeah, I am.
So my, I have two questions. First one is that you mentioned we can use tree to represent hash function. So we know that the hash function, along the hash function has to produce uniform random output and also security guarantees. So compare it to Merkle-Lambda construction, which absorbs the input step by step. So this tree absorbs the input at once, right? So how large this tree would have to be in order to guarantee the security guarantees. And
How large the tree should be in order to guarantee security? Is that your question? Yeah, but the tree itself doesn't matter too much. It's only made larger if the length of your message is larger, but the security comes from the compression part. So if you use this tree, so what's important is what you put inside here. Yeah? That should give you the security. That can again be block cipher based or like MD4 or things like that. Yeah.
And my second question is AES versus side channel attack. So we know that AES has some weaknesses, but it's not the algorithm, it's how you implement it. So is there something we can do with the AES so that it becomes independent of how you implement it to protect against side channel attacks?
Yeah, well, if you use this special instruction on the CPU, then you already are protected because it avoids all these exploits. Now, also if you read the literature on side channel attacks on AES, they often make quite strong assumptions about the power of the attacker. For most of them, the attacker needs to be able to run his software on your machine and needs to know exactly which programs are running on your machine and things like that. So I wouldn't worry too much about that. If it's on a smart card, where an attacker really can know all these things, then it's a matter of carefully designing the hardware such that there is no leakage. Yeah. But there is also known methods to do that. Okay, if there are no more questions, I've been asked to repeat the instructions. The people who had the industry registration, so paid a lot of money, will go with Professor Preneel eating over there. The other people who had a reduced fare need to go to Alma, but they need a voucher, otherwise they will not get food in the Alma, and they will get a voucher from Pela, I think. Yeah. Okay. Enjoy your meals.